Hello, everyone. This talk is called Hardness Condensation by Restriction, and this is joint work with Mika Gyosil, Newman, and Dmitry Sokolov. Okay, so let me illustrate what hardness condensation is without yet defining it concretely. So for example, you have a graph with some chromatic number. Chromatic number is the smallest number of colors you need to use to color the nodes such that no edge connects to nodes of the same color. So what it means to condense it? So I will think about it like this. So can you find a subgraph with the number of nodes depending on chromatic number such that it still has the original chromatic number of the entire graph? So for this graph, the chromatic number is 3, and yet if you look at graphs even containing 4 nodes, you never will find a graph with chromatic number 3. All these graphs will be forests because this graph has girth 5, so the smallest cycle has length 5, so no graph of size less than 5 can contain cycles, so it has chromatic number 2, right? So it was shown that this is true in general. So for fixed chromatic number, you can have arbitrarily large girth, so you never will see any subgraphs with chromatic number larger than 2 if you look at small subgraphs. Okay, so chromatic number is not condensable, right? So let me give an example of some graph theoretical notion which is condensable. So this notion is vertex cover. Vertex cover is a set of nodes such that each node is incident to, each edge is incident to a node in the vertex cover. Okay, so the question is the same. Can you witness it with a small subgraph? Can you find a subgraph such that its vertex cover is that of the original graph and the size of the graph only depends on the size of the vertex cover? Okay, so this is probably rings a bell. So it's from the field of fixed parameter tractability, and it's called kernelization. So you not necessarily find a subgraph there, but you map a pair large graph K to a pair graph which size only depends on K and some K prime such that it's a car production. So like the big graph has a vertex cover of size K if and only if the small graph has vertex cover of size K prime. And in this case, you can even do it with a subgraph of the original graph. Okay, so this is a positive example of hardness condensation. We can find a small substructure which sort of encapsulates the structure of the original problem. And in this talk, I will focus on a simple way of condensing query and communication complexity. So let me quickly define query complexity. Query complexity is a very nice notion. You have a function, and its query complexity is a number of bit probes you need to make until you learn the value of the function, right? So the optimal number of such bit probes. So let me illustrate it. So if you have a function disjunction, then one way to probe its bits to learn its value is just to probe it one by one until you find a one value, right? So this corresponds to this decision tree of sort of bamboo shape, right? So you query bits one by one until you find a one. And if you never find a one, the value is 0. So it's easy to show that it is optimal because no matter how you query the bits, if all the answers you get are zeros, that means that you don't know the value of the function yet until you query the entire input, because if the last bit is 0, the output is 0, and if it's 1, the output should be 1. So your O0 branch of your decision tree must have length n. Okay, so this is a simple example of function with maximum query complexity. So condensing query complexity for us would mean to restrict all but O of k, where k is the query complexity bits, such that the restricted function retains its original query complexity. So for OR, it's trivial because it already has maximum query complexity, so there's nothing to restrict. So let us consider some function with intermediate query complexity, so this notion can be interesting. So such function is called sync, one of such functions, and it's defined as follows. So as input, you are given a tournament graph. So it's a complete graph where between every pair of nodes, you have an edge with one of the directions, and these directions are given to you as input, and you can output 1 if and only if this graph contains a sink, so there is a node such that all edges that are incident to it directed towards it, right? So in this case, it's 1, and if there is no such node, it's 0. Okay, so so what is query complexity of such a function? It's not hard to show that it's linear. So we will show up lower bound and the upper bound to be an exercise, a nice one. And so showing lower bound is actually equivalent to condensing the function. So consider a node, say node number 1, and let us restrict all the edges which are not incident to it in such a way that there is a cycle spanning all the nodes except 1, right? So no node except 1 have a chance to be a sink now. So the restricted function is 1 if and only if the node number 1 is a sink, right? So if all edges which are colored yellow on the screen are directed towards it. So this is equivalent to AND function or OR function with some flipped bits, and we know that it has linear query complexity, right? So we just observe that first, sink has query complexity omega of n, and second, it can be restricted to its query complexity, right? Okay, so this is very nice, but what about the general case? So is it true for all functions? Can we always find such a restriction? And surprisingly, the answer is, I mean, I guess unsurprisingly, the answer is no, but it's surprisingly hard to find such a function. So this function that we found is based on cheat sheets, which have found many applications in separating different query complexity notions. And this is another application of this like off-the-shelf construction, which we found. Okay, so this is exciting. So query complexity cannot be condensed. So what about communication complexity? So let's start with deterministic communication complexity. Let me introduce the notion. So we have a function with 2 arguments. You can think about them as numbers from 1 to n. And there are 2 players, Alice and Bob. And Alice and Bob each have one of the numbers. And they want to exchange messages such that after the exchange, they both know the value of the function. So abstractly, you can think about it like this. So there is a matrix containing all the values of the function f, and by each communicated bit, Alice sort of partitions the rows of the matrix into 2 sets, right? The green set is where Alice communicated 1, and blue where she communicated 0. Right, so in each of these cases, Bob also communicates a bit, and then he thereby partitions these rectangles into two still smaller rectangles, right? So this is a description of communication protocol. So they continue like this until they both know the value of the function. What does it mean? It means that the current rectangle that they have is monochromatic. So each deterministic communication protocol induces a partition of a matrix into monochromatic rectangles. Notice that not every partition into monochromatic rectangles. Notice 2 things. First, that not every partition corresponds to communication protocol, and that not and then these rectangles are not geometric as I drawn on this picture, but combinatorial, right? Okay, so from this, you can notice that deterministic communication complexity is at least log of rank of the matrix, because each of these rectangles is a rank at most 1 matrix. So our communication matrix is the sum of these rank 1 matrices, and there are about 2 to the communication complexity of this rectangle. So that's where we get our inequality. And famous log rank conjecture says that this inequality holds in the opposite direction, but maybe with some polynomial multiplier. So communication complexity can be upper bounded by log rank to some power c. Okay, this is very widely open, and but let me connect it to condensation. So what is a condensation for deterministic communication complexity? Here, we need to find a matrix, a submatrix of our initial communication matrix M, which retains the original communication complexity while being of size 2 to the k by 2 to the k. Okay, so notice that for rank, this is doable, right? So for every rank K matrix, we can find K by K matrix of full rank. So this is another example of hardness condensation. And hence, since we found if log rank conjecture is true, then we could at least weakly condense deterministic communication. Very surprisingly, and very recently, Gruby showed that without proving log rank conjecture, that this is true. So you can weakly condense communication complexity. So you can find a submatrix of appropriate size of with deterministic communication complexity square root of the original one. And this is very exciting. Nevertheless, the original problem remains open. So can we losslessly condense it? So can we find the submatrix of size 2 to the k by 2 to the k, which retains the original communication complexity? Okay, so as a side result, we show that lifting from query complexity, which is a technique which worked for many to solve many open problems in communication recently, this technique fails, which means that all lifted matrices are condensable. Okay, but it's just a side note. If you didn't understand, don't worry. Okay, so from deterministic communication, let us move to randomized communication. The model is the same, but now Alice and Bob have access to an infinite string of random bits. And using this infinite string, then they, for example, can use hashing, and using hashing, they can compute functions which are difficult for deterministic communication complexity. So one such function is greater than, so it's just function compared to numbers if Alice number is larger than output 1, if it's not output 0. Right, so this function has randomized communication complexity log n, and deterministic communication complexity is maximum possible, which is log of the range. Okay, so, and from this example, we also get that randomized communication cannot really be condensed, because if you take a function of a submatrix of dimension 2 to the log n times 2 to the log n, we get that this submatrix is still a matrix of form greater than, right? It's not hard to show that this sort of upper triangle matrix, and we still have such a matrix. So thus, this matrix has a very small query complexity, communication complexity. It's log n, right? Because greater than on range n has communication complexity log n, so we still exponentially fall from there. So we cannot condense function greater than. And if you're not satisfied with this, there is even more drastic example by Hamajumyan, Hatami, and Hatami, who prove that you can have almost optimal communication complexity, and yet all your submatrices have of very moderate size have, I mean, moderately small size, have already constant cost communication. Okay, so randomized communication complexity cannot really be condensed even in a very weak sense, but we found some interesting example where it can. So I told you about log rank conjecture. There was also log approximate rank conjecture, which related randomized communication with approximate rank, which is a appropriate notion for this inequality, which I'm not going to define. Okay, but so log approximate rank conjecture was disproved pretty recently with a very simple function. So its function is sync of XOR. So Alice and Bob both have the inputs, they XOR it bit by bit, and they compute the sync function that is seen for on this XOR. Okay, so this function has communication complexity linear in the number of nodes in the graph, but approximate rank for this function is very low. It's polynomial. So log of this rank is much smaller than randomized communication. So the intersecting subset of the authors were interested in improving this separation. So they wanted to turn n to the fourth to n to the cube, and they proposed some sophisticated method of doing so. But we are able to prove their desired separation simply by condensing the original function. So we show that you can condense this function sync of XOR to the matrix of size 2 to the n by 2 to the n, such that it retains the original query complexity, and it's not hard to show that for any matrix of such size, approximate rank falls n-fold. Okay, so this is a nice application of this condensability, and it shows that it is really rich notion, right? So usually it's completely false, but in this very important example, it turned out to be true in a very strong sense. Okay, so let me conclude with some summary and open problems. So query complexity is not losslessly condensable by restriction. Randomized communication complexity is not even weakly condensable, and a deterministic one is weakly condensable, but we don't really know if it's condensable losslessly. So another point is that to condense sync of XOR matrix, we used some nice technical notion, which we call Shearer extractor, and it is very interesting to see if they find other applications. So this is it for me. Thanks a lot.